From the collapse of interstellar dust clouds in the furthest recesses of space to the palm of our hands, elements in the periodic table travel great distances to go from early formation in the universe to their final resting place in our everyday technology. Smartphones, for example, are made up of more than 60 different elements, over 2/3 of the periodic table. In this video, we will dive deep into one of these elements, arsenic, and uncover the truth about its life cycle from cosmic formation all the way to smartphones in our pockets. Light elements like hydrogen and helium are formed through fusion in the core of stars. However, having an atomic number of 33, or 33 protons in its core, arsenic is too heavy to be formed in this way. Instead, it forms through a process known as neutron capture, most commonly seen in older, giant stars. During neutron capture, elements with smaller nuclei are bombarded with neutrons, which are converted to protons upon impact with the element's atomic core. The addition of protons in the nucleus, commonly referred to as beta decay, causes the fundamental structure of the atoms to be altered. Elements like zinc and germanium will undergo this neutron bombardment until they are finally transformed into heavier elements like arsenic. After the formation of arsenic within these stellar processes, it is finally ejected into space via supernova and carried through space by stellar winds along with interstellar dust and gas. Now that we've uncovered the truth of our chosen element's formation, we can move to the next step of its life cycle as it makes its way to our planet. But in order to do that, we need to first look at how Earth was formed 4.56 billion years ago. In truth, our story begins even earlier than that, with the formation of our solar system. Before the existence of the Sun, the Earth, and our 7 planetary neighbors, our solar system was nothing more than a cloud of interstellar gas and dust, remnants of supernovas from earlier generations of stars. Over time, this dust cloud began to collapse under its own weight, causing it to spin and form a disc-like shape. From the most densely packed center of this disc, the Sun began to form. As it grew, it absorbed more and more gas and dust from its surroundings, until finally reaching its desired size. However, not all material got absorbed by the Sun. The remaining material continued to orbit the Sun and condense into many smaller masses, forming planets. As Earth grew in size and gravitation, in a manner similar to that of the Sun, the rotational energy transferred to heat energy, causing the separation of heavier and lighter elements to the Earth's upper and lower interior layers, known as differentiation. But how does this apply to the life cycle of elements? Well, take ours, for example. Located in the interstellar dust cloud, arsenic was incorporated into the formation of Earth, and as a lighter element, was pushed upwards through differentiation, leaving it abundant in our planet's surface. Because of its abundance in Earth's crust, arsenic is most commonly sourced from mining. It is found in gold deposits rich in sulfide minerals like arsenopyrite, aptly named for its arsenic abundance. Being the world leader in mining, China produces over 60% of the world's arsenic through methods like open pit mining and underground mining. After the arsenic-rich ore has been mined, it's extracted through a long process during which the metal ore is crushed and heated to release arsenic in the form of trioxide gas, which is then condensed and prepared for industry use. This process can be extremely dangerous and hazardous for workers, as well as nearby communities and ecosystems due to the risk of releasing toxic gas into the atmosphere if not properly controlled. Now that our element has made it all the way from the center of an interstellar dust cloud to a factory-made building material, the last step of arsenic's journey is to be applied to its ultimate industrial use. Often used in manufacturing of electronics, arsenic can be used in the form of gallium arsenide for high-frequency components of smartphones, such as high-speed microchips and infrared lights. This is possible because of the element's unique chemical properties that allow electrical energy to be efficiently converted into light. Without arsenic, our smartphones wouldn't be nearly as fast or capable as they are today. And to think the arsenic that's in your phone was once floating out in space billions of years ago, long before phones, humans, or even our solar system ever existed. Now that we've uncovered the truth of arsenic's long and arduous journey across time and space, we now know the full story of the element's origin, and maybe even a little bit about our own origin. I hope you learned something, and thanks for watching.